So we're going to be reviewing compound pendulums. In a way, we covered what these are roughly in the rigid bodies chapter, and a compound pendulum is essentially just a rigid body. My God, a rigid body acting sort of as a pendulum in a way. So it can be shown that the time to complete an oscillation by a compound pendulum is 2 pi square root of I, which remember is the moment of inertia, divided by mgh, which you might actually recognize as gravitational potential energy, which is quite a fun relationship. Now this is what the diagram would look like. I can't actually remember, I couldn't remember the proof of this because the proof is actually quite long, so I actually typed it all out. So this is roughly what it looked like, where C is the center of gravity, and O is essentially the point where the reaction force is. The distance between them is h, and it's going to be swinging in a positive way, so in a positive direction. And R is obviously the reaction force from the point at which it's swinging. So you can clearly see that it's quite a lot, and it actually does use a small angle approximation in it somewhere. So the forces on the body are the reaction R and the weight mg, which occurs through the COG. So the moment about R is 0, mostly because it's not flying anywhere. It's sort of stationed such that such that R is constant. And the line of action from the center of gravity to mg, in a way, is h sine theta. So with the principle of conservation of angular momentum, we know that this m is the moment of inertia times the second derivative of the angle with respect to time, which we can actually rewrite as minus mg h sine theta, which is what we get from this. So I'll actually write this. So this is mg, and then we get h sine theta acting here, and then h cos theta there. And then obviously for small theta, because they're performing small oscillations, sine theta is approximately theta. And then we end up with d2 theta by dt squared is minus mgh over I theta, just from dividing by I. Now, of course, we know that at this point, should know that the second derivative of position with respect to time is proportional to negative of displacement. And we also know there that omega squared is mgh divided by I from here. So this would actually act as our omega squared. Hence the periodic time will be t divided by this, which after we do it and take the square root, we end up with t is 2 pi root I over mgh. It is quite a complex proof that you don't necessarily need to know. Like, I couldn't even remember. I had to re-look up how to derive this. It is a bit mental, but you just need to know that t is 2 pi square root of I over mgh for all intents and purposes.